Welcome to Lecture 3 on Engineering Thermodynamics. In this session, we are going to discuss topics such as Continuum Concept, Pressure Measurement, Temperature Measurement, Thermodynamic Work, and Displacement Work. Coming to the Continuum Concept, in the very first lecture, we discussed about classical thermodynamics and statistical thermodynamics. It is convenient for us to adapt classical thermodynamics than statistical thermodynamics, as the statistical thermodynamics deals at the microscopic level of the system. If the volume of the system considered for study is considerably large when compared to the dimensions of the molecules, then classical thermodynamics or macroscopic approach can be used and the results of the analysis will be convincing or error-free. However, if the dimensions of the system taken for the study is comparable with the molecular dimensions, then classical thermodynamics or macroscopic approach cannot be applied. This is given by the continuum concept. According to continuum concept, the substance or matter within the system should be distributed continuously without any voids or empty spaces. Now let us consider a system, and this is the region of the system which is considered for analysis is having volume V1, and this volume V1 is larger volume and it is going to have infinite number of molecules. Within this control volume, on an average, the number of molecules will not have much variation at any instant, and hence the density is going to be constant. So density of the substance within this volume is given as rho equal to m by v, where m is the mass of the substance and v1 is the volume of the system. Now when the volume of the system is going to be decreased from v1, and assume that we are going to decrease the volume by a smaller quantity of dv, the smaller volume dv, then the final volume will become v1 minus dv. And the density will become rho equal to m minus dm divided by v1 minus dv. And still the density of, after reducing the volume, the density of the system will also be equal to the density of the initial system. Further, if you are going to reduce the volume again by dv amount, then the sufficient number of molecules will be available inside the volume of the system and the density is going to be maintained constant. If we keep on proceeding by reducing the volume, and a stage is going to be reached where the volume of the system is going to be V2, and beyond this volume, if you reduce the volume of the system, then the density may increase or decrease at any particular instant, because as the number of molecules available in the smaller volume is few, and also the density changes as the volume of the system is less than volume V2, and the volume is going to contain rarefied gases. For this condition of rarefied gases, we have to apply only rarefied gas flow theory, or we have to apply the microscopic approach in order to study the behavior of the system or to determine the properties of the system. So we mean to say that the continuum concept can be applied up to a volume of V2, and lesser than the volume V2, the continuum concept cannot be applied. So in this diagram we can see this is a system, and this is the region, this circular region, where we are going to consider the density of the system, right, which contains many number of molecules. If you keep on decreasing the size of the volume, if you keep on reduce the radius of the this spherical container having the molecules of the system, then a particular volume is going to be reached, and beyond that we cannot have the continuum concept. The same thing can be explained using the density versus volume diagram. Now in the initial case, when the volume is V1, volume is V1, at this point we had many number of molecules within the system, and the density at any particular instant is going to be constant. As we keep on reducing the volume from point B, let us say it has come to state A, from state B it has come to state A, the system has come to state A, and up to which we can apply the continuum concept, right, or we can go for the classical thermodynamics approach. and beyond this state A, once at state A the volume is V2. If you further reduce the volume of the system, then the density will not remain constant. Instead, it can either decrease or it can either increase, because the amount of molecule that is present inside this volume is going to vary with respect to time. If very few molecules are going to be present with a volume lesser than V2, then let us say in this diagram we have mentioned 4 molecules are going to be there, and at a particular instant, then in the next instant it can be 3 or it can be 5. So the number of molecules is going to vary at any particular instant. So there is a limit for the volume with which we can adapt or we can apply the classical thermodynamics. So that is what is given by the continuum concept. So up to this we say that the matter that is considered is going to be continuous and there are no much voids are going to be there. The next topic is pressure measurement. So from physics we know that pressure is nothing but force applied per unit area, and to measure the pressure we have two different scales. There are two different scales available. One we call it as a relative scale and the other one is called as an absolute scale. In the case of a relative scale, atmospheric pressure is kept as the reference, and the pressure above atmospheric pressure, is called as positive pressure or gauge pressure, and the pressure less than atmospheric pressure is called as negative pressure or vacuum pressure. Whereas in the case of absolute scale, absolute zero pressure is kept as the reference. So in the case of absolute pressure, we are not going to have any, in the case of absolute scale, we are not going to have any negative value because 0 is the minimum value in the absolute scale. To explain the difference between these two, relative scale and absolute scale, you consider a pen stand. Inside the pen stand there is a pen. Assume that the height of the pen stand is 5 centimeter, and now I am going to measure the height of the pen from the top of the pen stand. Assume that the distance, when I measure the height of the pen from the top of the pen stand, let us say it is 8 centimeter. So the total height is 5 plus 8, which is 13 centimeter. So if you are going to measure from the top of the pen stand the height of the pen, then that measurement is what we call it as relative scale measurement. Instead, if you are going to measure the pen from the bottom of the pen to the full length, that we call it as absolute scale. So here, if you want to convert the relative scale into absolute scale, then what we have to do? We have to add the reference value. In this case, in the case of pen stand, the height of the pen stand is the reference value, which is 5 centimeter plus 8 centimeter is the height of the pen. Totally it is going to be 13 centimeter. So in the case of measuring pressure, if you are going to have a relative scale, that means we have measured the pressure with reference to the atmospheric pressure, then we have to add the value of the atmospheric pressure to the gauge pressure. Only then we will get the absolute pressure. If you are going to have, if you want to measure the negative pressure or vacuum pressure, now for this you can consider, let us say we are having an eraser which is present inside the pen stand vertically, and the height of the eraser, the top of the eraser from the top of the pen stand, if I am going to measure, let us say it is going to show 2 centimeters. That means the absolute value is 3 centimeters. That is the height of the eraser, because the total height of the pen stand is 5 centimeter, and from the top of the pen stand to the top of the eraser it is 2 centimeter. So the absolute value of the eraser or the absolute height of the eraser is 3 centimeter. So in this case, what we have done, from the reference we have subtracted the value from the reference to the height of the eraser. So if you want to measure the negative pressure or vacuum pressure in terms of absolute value, then in absolute scale, then it is going to be the atmospheric pressure minus the vacuum gauge reading. Okay, so now if you want to convert from absolute scale to relative scale, then for positive pressure, if you want the gauge pressure value, then the to calculate the gauge pressure, if you know the absolute pressure, then it is absolute pressure minus atmospheric pressure. Similarly, for negative pressure, if you want to measure the vacuum gauge value or the negative pressure value, then it is atmospheric pressure minus the absolute pressure. So this we will explain in detail by representing the the atmospheric pressure scale as well as the absolute pressure, right? So now you consider this diagram. So here we are having two reference values. One is the atmospheric pressure. This line represents the atmospheric pressure, whereas the another reference is the absolute pressure line. Okay. So now to measure a pressure above the atmospheric pressure, you consider this is the pressure which I want to measure, right? This much is the increase in pressure when compared to the atmospheric pressure. And already with reference to the absolute zero pressure, atmospheric pressure is already at this value. So if you want to convert this relative scale into absolute pressure, then we have to add the height of this to this. So your absolute pressure for a gauge pressure value or a positive pressure value is going to be sum of the atmospheric pressure plus the gauge pressure. That will give you the value of the pressure in an absolute scale. Now let us say we have a negative pressure. So this is the pressure indicated by the vacuum gauge. So this is with reference to the atmospheric pressure. This is the value that is available. So now if you want to convert this value into absolute pressure, then we have to subtract this value from the atmospheric pressure. So which is nothing but this is the absolute pressure value. Okay. So there are two references. One is the absolute zero pressure as being kept as reference, and other one is the atmospheric pressure being kept as the reference. If the atmospheric pressure is going to be the reference, then the pressure that is going to be measured is called as, it is based on the relative scale, whereas if the absolute zero pressure is going to be the reference value, then the pressure measured is called as absolute pressure. To measure the pressure, we have devices called pressure gauges, right? So these pressure gauges indicate the pressure higher than the atmospheric pressure. So if you want to convert the value indicated by the pressure gauge into absolute pressure, then we have to add atmospheric pressure to this. And the vacuum gauges are used to measure pressure less than the atmospheric pressure. So this will indicate to what extent the pressure is less than the atmospheric pressure. So this this handle will move in the clockwise direction, whereas in the case of vacuum gauge, the handle will move in the anti-clockwise direction. And we have a device called barometer. This is used to measure the atmospheric pressure. So these are some of the pressure measuring devices. Coming to the atmospheric pressure, so we have various units to represent pressure. So one atmospheric pressure in terms of Newton per meter square is 1.01325 into 10 power 5. And if you want to represent in bar, so 1 Newton per meter square is nothing but 1 bar. So atmospheric pressure in terms of bar is 1.01325 bar. The same atmospheric pressure if you want to express in Pascal. Pascal is the SI unit for pressure, and 1 Pascal is nothing but 1 Newton per meter square. So therefore 1 atmospheric pressure is 1.01325 into 10 raised to the power 5 Pascal. If you express this in kilopascal, then it is going to be 101.325 kilopascal. In terms of megapascal, megapascal is 10 power 6 Pascal. So it is going to be 0.101325 megapascal. In terms of dyne per centimeter square, the value is 1.01325 into 10 to the power 6 dyne per centimeter square. And the atmospheric pressure value in kilogram force per centimeter square, kg per centimeter square, is 1.03323 kg per centimeter square. In terms of pounds per square inch, atmospheric pressure value is 14.7. In terms of meters of water column, atmospheric pressure value is 10.3 meters. And atmospheric pressure value is equal to 760 mm of mercury. Mm of mercury is also called as tar. So these are the units of pressure. It can be expressed in Pascal. In SI unit, we express pressure in terms of Pascal. We can express pressure in terms of Newton per meter square, or bar, or kg per centimeter square, or pounds per square inch, or meters of water column, or tar, or dyne per centimeter square. To measure temperature, right? In order to measure temperature, also we have two scales, like both relative scale and absolute scale. Under relative scale also we have two scales. One we call it as Celsius scale, other one we call it as Fahrenheit scale. To measure temperature in absolute scale also we have again two scales are available. One we call it as Kelvin scale and the other one is called Rankine scale. So this Celsius scale was developed by Anders Celsius. He named the scale as centigrade scale, and later in order to honor Celsius, the scale was renamed as Celsius scale. So Anders Celsius, he is a Swedish astronomer, and the unit used is degree C, and if you want to convert this degree C into Kelvin, into absolute temperature, then we have to add 273.15, right? That means 0 degree C equal to 273.15 Kelvin. In the absolute scale or in the Kelvin scale, the unit is K or Kelvin. So this is to honor Lord Kelvin. This unit is used. So absolute zero temperature is the reference in this case. So when we say absolute zero temperature is the reference, then you cannot have a negative value in the absolute scale. And for while writing the temperature in Kelvin scale, remember that we should not use degree symbol. Coming to Fahrenheit scale, this is a relative scale. This was developed by Daniel Gabriel Fahrenheit. He is a German instrument maker and the unit is degree F. And if you want to convert from Fahrenheit to degree C, then it is F minus 32 into 5 by 9. This will give you the value of temperature in Fahrenheit to Celsius. And also remember that at minus 40 degrees C, the Fahrenheit scale and Celsius scale will show the same reading. And if you want to convert, coming to the absolute scale, Rankine scale, the unit is degree Rankine, and 0 degree Rankine is minus 459.67 degree Fahrenheit, or 0 degree Fahrenheit is 459.67 degree Rankine. So if you want to convert a reading in degree Fahrenheit into degree Rankine, then we have to add 459.67. At absolute zero temperature, your Kelvin scale and Rankine scale will show same value, right, at absolute zero. So 0 Kelvin is equal to 0 degree Rankine. So if you want to convert degree Rankine into Kelvin, then we have to multiply by 5 by 9. So these are some of the scales that are available to measure the temperature. And the various devices available to measure temperatures are thermometer, and this is infrared thermometer. This is a mercury field thermometer. This is a digital thermometer. This is a thermocouple. Thermocouple has two dissimilar metal which are connected, and when the junction of the two dissimilar metals are going to be heated, then an EMF is going to be generated, or a voltage is going to be generated. So depending upon the difference in temperature, the amount of voltage generated is going to vary, based on which we can measure the temperature. And there are devices such as Langmuir probe. These are used to measure the temperature of the electron or temperature of the plasma. And other thermodynamic devices like RTD, thermistor are also available to measure the temperature. And coming to the topic on work transfer, from physics or mechanics, we know that work transfer is given as product of force into distance traveled. Whereas in thermodynamics, work is defined like this. Work is said to be done by a system if the sole effect external to the system is to raise a weight against the gravity. That means in the case of thermodynamics, we will accept work is being done provided if the sole effect external to the system is able to lift a weight against the gravity. So now you consider a battery which is connected to an electric motor, and the motor is also coupled to a fan or a blade. So when you are going to connect the power supply from the battery to the motor, the shaft of the motor is going to rotate, and the blade is connected to this, so this blade is also going to rotate. It is going to spin. Okay, this is the complete diagram which indicates the battery connected to the electric motor and driving a fan. So this shows that work is being done. But in thermodynamics, to accept whether to accept that work is being done in this case, what they used to do is that we have to prove that this system is able to lift a weight against the gravity. So now let us consider a battery, the same battery, and we are going to connect this battery to an electric motor, and the shaft of the electric motor is going to rotate. Now assume that this I am going to consider as a system, and external to the system I am going to couple a pulley to the shaft of the electric motor. So external to this, a pulley is being connected, and I am going to attach a string to this pulley, and the other end of the string is connected to a weight. Now when we allow the motor to rotate by supplying electric power from the battery, and as the pulley rotates, the string is going to be wound over the pulley. As a result, the weight is going to be lifted up. Against the gravity, it is going to lift up. So thereby now we are proving that a battery connected to a fan through an electric motor, it does a thermodynamic work. So because we are able to prove that it is able to lift a weight against the gravity. Coming to displacement work. Displacement work is also called as PDV work. To explain this displacement work, let us consider a cylinder piston arrangement containing a gas. So this is the cylinder and this is the piston. Okay. So within the cylinder piston arrangement, a gas is present. Now assume that piston is at state 1. When the piston is at state 1, that means the gas inside the cylinder is compressed and the pressure of the gas is P1 and the volume is V1. Right. So initial state is state 1. Now when it is pressure, when the piston is at state 1, the pressure inside this is higher than the atmospheric pressure. So if you leave this, then what will happen? Since the pressure is higher than the atmospheric pressure, the gas inside the cylinder piston arrangement will start to expand. When it starts to expand, and assume that it is going to reach state 2, where the equilibrium is going to be maintained between the pressure of the system and the surrounding. So at state 2, the pressure is P2, and at state 2, the volume is V2. The area of cross section of the piston is, let us say it is A. Okay. So this is the, now this complete process, when the system expands from state 1 to 2, I am going to represent in a pressure volume diagram. So initial state is state 1, where pressure is P1 and volume is V1. That means volume is less, pressure is high. And we have allowed the piston to expand. We have allowed the gas to expand, thereby the piston is going to move towards the right direction. When it moves in the right hand direction, as the gas expands, the pressure is going to decrease and volume is going to increase, and the final state reached by the system is state 2, where pressure is P2. Now pressure has come down, P2 is less than P1, and corresponding at state 2, the volume is V2, which is higher than volume 1. Okay. So now I want to determine the work done during this process, right? So for that, let us consider an intermediate state, and at this intermediate state, pressure is P, right? Initial state pressure is P1, final state pressure is P2, intermediate state pressure is P. And assume that there is a small change in volume as the piston moves. I am going to consider two intermediate states, right? And the distance traveled by the piston is dl, small distance dl, and the corresponding swept volume is dv, right? So for this movement of infinitesimal distance dl, I want to calculate what is the force acting on the piston. So force is given as pressure into area, and to determine the infinitesimal work for this movement of dl, right? For the movement of dl or for a swept volume of dv, the work done during this is, work is force into distance travel. This smaller work dw is F into dl, and force is nothing but pressure into area. So replacing F by P into A, we will get PA dl. This A is, we are having the uniform area of cross section, so therefore area is constant. So this area can be taken inside the derivative. So if you take area inside the derivative, then it will become A into L. So area of cross section into the stroke length. So area into stroke length will give you the volume. So this is P into, within the derivative, V. So the work done, the smaller work done, infinitesimal work done between the two intermediate state is given as dw equal to P into dv. So if you want to calculate the total work done during the change of state from state 1 to state 2, then we have to integrate this. So integral dv from state 1 to 2, that is the total work done for change of state from 1 to 2. So it is integral from state 1 to 2 pdv, right? At state 1 volume is V1, at state 2 volume is V2. So the total work done during this change of state from 1 to 2 is integral V1 to V2 PdV. So this PdV refers to, this is dV and this is the pressure at the intermediate state. So this P into dV, it represents the area under this diagram, right? Or integral V1 to V2 PdV is the complete area under the PV diagram. So the work done during this process is given as area under the curve in a PV diagram. And remember this integral PdV expression for work. The expression for work integral PdV, this is applicable for a quasi-static process, right? And also remember that here we have considered a closed system. So for a closed system, if you want to calculate the work, provided if the closed system is going to undergo a quasi-static process, then we can apply integral PdV to get the work done when the system undergoes a change of state from state 1 to 2. Right? Or we can say that the area under the curve in a PV diagram represents work transfer.